Hello everyone. I'm Kazu from KK, and today I'm questioning the result you here just showed. Like the level has a factor of 5 or 3 better on the constraining of sigma 8. And I recently posted the paper on the archive, and if you are interested in details, please just check this paper out. Okay, so this is my outline. So I'll begin with some short introduction of what is a field level inference. But although I assume almost all you know what is a field level inference here. And then I will move on to my main topic, which is the comparison of this field level inference with the conventional power spectrum plus bispectrum analysis. And I would argue that in the standard setup, in the perturbative regime, the power spectrum plus bispectrum would give you a almost comparable constraining power of the field level inference in some idealized setting. And also for practical application, there's some big challenge in the field level inference. And in that case, the field P plus B would be more kind of stable. That's my kind of takeaway. Okay, so let me start with super basic stuff. So in cosmology, what we can do is basically predict some statistical property of the initial conditions. I mean, given some cosmological parameters, you cannot predict kind of realization of the initial conditions. Rather, what we can do is just predict power spectrum of the initial conditions, and then given the power spectrum, we can generate some realization of the initial conditions. Then, given realization of this initial condition, we can evolve them into the final density field at the map level or field level, using perturbation theory or like n-body simulation, whatever you want to use. Then our task is to compare this theoretical prediction with the real data, and the big issue we have to manage is we don't know the realization of initial conditions, so we have to marginalize over them. So in the field level inference or the usual power spectrum bispectrum analysis. So in the standard analysis, we did it kind of implicitly, right? So we first take over the ensemble average, right? This means marginalization of the initial conditions. So the summary statistics is a marginal kind of some statistics that marginalize over the unknown initial conditions with some known weight. On the other hand, in the field level inference, we try to marginalize over the initial condition explicitly. I would call it the field level inference, by the way. So we have to have some prediction on the map level, as Yulia said, and we are trying to compare the theoretical prediction at each voxel or each Fourier mode with some data at each Fourier mode. So the point is, we marginalize over the initial condition after comparing the theorem data. So we will have some joint posterior distribution of the cosmological parameters and initial conditions explicitly, then marginalize over the initial condition numerically. This is of course a big challenge, but nowadays kind of this is a doable stuff. So here's some demo I made, although I didn't put any fancy name on my code, but my code is working this kind of way. I mean, first we sample cosmological parameter, then compute the linear power spectrum, then generalize some random field, and evolve them into some final observable based on some perturbation theory, and compare the observables with data at the level of the field, and evaluate the likelihood, then go back to the sampling the initial, cosmological parameters. Okay. So this is what field level inference is doing. Now, while we are working on this project, this, I would say, kind of controversial paper came out. It says, if you do a field level inference with perturbative forward modeling at the scale of scale 0.1 or 0.12, then you would get like factor of 3 or 5 improvement on the constraint on the sigma 8. So the natural question, already some guy asked, but natural question is, where does this information come from? So to answer this question, it's better to kind of work on some toy model, as usually physicists do. So we'd like to kind of compare field level inference with a power spectrum plus bispectrum with some theoretically well under control examples. So what we do is kind of apple-to-apple comparison. We generate some mock data based on flawed model, which uses perturbation theory, and this perturbation theory would be used in the power spectrum plus bispectrum analysis as well as the field level inference. I mean, the flawed model I use is the same in the power spectrum and bispectrum analysis and the field level inference. And also, to avoid the discussion about the likelihood of this field level inference, we added some white Gaussian noise by hand on the mock data to make the field level likelihood Gaussian. So we assume the likelihood for the field level inference in Gaussian, and also for the power spectrum bispectrum, but with a different reason. Anyway, so we compare this field level inference and power spectrum plus bispectrum analysis with the same K-max in the likelihood. Okay? And to begin with, this is a simplest example where we compare the field level inference and power spectrum with a linear Gaussian random field. In this case, of course, we know the compression into the power spectrum is kind of lossless. So the field level inference should give you the same answer as the power spectrum, and it does. This is kind of just a sanity check, but this shows my code is not junk. So let's move on to the a bit more complicated scenario where I added just one quadratic piece in the mock data of flawed model. So, and did a kind of comparison between the power spectrum and field level inference. Some people might think that in this case, now we have a kind of non-Gaussian field, then constraining power of the power spectrum can be worse than the field level. But this is not the case. As I showed here, so this is just some contour for the cosmological parameters, and gray is a power spectrum, blue is a field level, and they are kind of essentially the same. One say, okay, this is just toy model, too simplistic. So I can show you some more realistic case where we did the same test for one LPT example. So this is a good proxy for nonlinear matter density field or large scales. Oh, by the way, we are comparing this K-max of 0.12. So this is a perturbative regime, right? So regarding for the constraining power on the cosmological parameter, they are again essentially the same, right? Why? This is kind of expected because again, we are working in the perturbative regime. But what this perturbative regime means is there's some small parameter that we use as a perturbative expansion. And if you look at the, for example, signal to noise, this is cumulative signal to noise for the power spectrum and bispectrum. So this is K-max and the signal to noise. And it's hard to see, but there's some blue line, blue curve on the top. And this is a signal to noise of the power spectrum. But if you compute the signal to noise of the bispectrum, the signal to noise for the bispectrum is much smaller than the power spectrum. And a factor of 10 smaller than the power spectrum, right? At perturbative regime, I'd say. And of course, we can kind of extract some information, some cosmological information from the bispectrum because we now have non-zero bispectrum. But if you try this bispectrum analysis, the constraining power of the bispectrum is much smaller than the power spectrum, reflected by this signal to noise comparison. And another important point I'd like to make here is in this case, as long as you focus on the cosmological parameters, there's no parameter break degeneracy if you add the bispectrum. I mean, the parameter degeneracy direction is the same as the power spectrum. This is why in this toy model, bispectrum doesn't help. And of course, the field level is equivalent to the power spectrum in this case. But of course, in reality, we know adding bispectrum helps the parameter constraint. So a simple example we can test with this toy model is to vary the noise amplitude in addition to the cosmological parameters. So as I said, the mock data I created has only the Gaussian noise. So this noise doesn't contribute to the bispectrum. In this case, if you look at the power spectrum and bispectrum constraint, the power spectrum constraint, power spectrum consists of the signal plus noise. So the noise would be degenerate with the signal part. And this is actually what's happening here. So if you look at the power spectrum constraint, which is shown by gray, is kind of larger than the constraining power from the field level inference shown by blue. But now, as I said, probably what's happening here is the degeneracy between noise parameter here with other cosmological parameters. So, but if you look at bispectrum doesn't have noise contribution. So probably adding bispectrum would break this degeneracy to recover the field level inference. Then actually this is the case. If we do the power spectrum plus bispectrum analysis for this example, then the P plus B looks equivalent to the field level. Of course, this is not kind of realistic scenario. Although this is still kind of toy model, but we can kind of move on to the more realistic case where we start to vary the linear bias. So as you know, at the linear field level or linear level, this linear bias is completely degenerate with amplitude of the density field. So only hope to break this degeneracy is, of course, in G2 quadratic term. In terms of the power spectrum, it can be expressed by the one-loop power spectrum. Of course, we can try the power spectrum analysis with this one-loop term, but the result is kind of nightmare, so which is shown by gray. There's a huge degeneracy. And of course, in this case, field level looks much better, like factor of 5 or 10. But again, we know bispectrum is quite useful to break this B1A degeneracy. So if we do this P plus B analysis, then again, this P plus B contour by green is essentially the same as the field level contours. So then, what's the lessons? Lessons kind of simple and kind of as expected. So in the perturbative regime, again, we have some perturbative parameter which is small, and all the higher order effect, higher order loops, higher order correlators like trispectrum, is suppressed by this variance of matter density, right? So as I showed, the signal to noise of the bispectrum much smaller than the power spectrum, and bispectrum only helps the constraining of the power spectrum if they have some information that breaks the degeneracy in the power spectrum. And without any calculation, you'd guess the signal to noise of the trispectrum is again smaller than the bispectrum, which should be order 1 at this scale. And if you add the trispectrum to the analysis, you need to include, for example, cubic order bias. Then intuitively, this won't help the constraint. Okay? But of course, that example I showed is just toy model, far from the reality. So, but the difference between my toy model and the kind of realistic Ford model would be just, it would be summarized in 2 points. The first point is just correct gravitational evolution. In my toy example, I didn't include any real, gravitational evolution. And B is probably second order or cubic order bias can play an important role. So actually we did these checks. We included some LPT displacement and also included the quadratic order bias, but the result doesn't change. So here I'm showing the result from some kind of zero-bridge plus quadratic galaxy bias, and red is a power spectrum plus bispectrum, and blue is a field level, and again, they are essentially the same. Same means order 10% difference, not factor of 3 or 5. The reason is the same, we are working in the perturbative regime. Okay, so I'll say something about some challenge in the field level inference. So far, I assumed the Gaussian likelihood for the field level inference, and by doing so, I kind of added the Gaussian noise by hand on the mock, but from the kind of perturbation theory, we know that residual noise is not Gaussian, right? So if you write down some part of the expansion to scarcity density field, we will have some stochasticity, and this epsilon is a kind of also the stochasticity, but it can have like 3-point function, 4-point function, not Gaussian, and also we have a density dependence, blah, blah, blah. So we know this residual is not Gaussian. So of course, this assumption of the Gaussian likelihood can't be true. So we can do, again, simple test with toy model. So we change the mock data by replacing the Gaussian noise by some Poisson noise, but still assuming the Gaussian likelihood for the field level. What would happen? So let me, again, start with a simplest example where we are only interested in the cosmological parameters. And in this case, although now we assume the wrong likelihood for the field level, the result is not biased, and error bar is kind of consistent with the power spectrum, as I discussed. So this means kind of as long as you rely on the information on the power spectrum for linear field, then a higher order noise contribution can be safely neglected. But if you start to vary, for example, linear bias in this example, where we start to use some information in the bispectrum, then result is kind of biased. So I'm showing it's hard to see, but there's some orange contour behind, which is field level, and which kind of overlaps with that contour I will explain later. So this contour is kind of biased from the true value. And why? We can interpret it in a simple way. So in terms of power spectrum plus bispectrum, the assumption of this Gaussian likelihood means you are neglecting the noise contribution in the bispectrum, a 3-point function. So this means Gaussian likelihood field level inference is equivalent to the P plus B analysis without this noise bispectrum. And this is again confirmed by this contour. So red is a P plus B analysis without this noise bispectrum, and they are kind of overlapped. But in the power spectrum bispectrum analysis, we can compute this bispectrum noise, and we can include them in the theoretical template while still using the Gaussian likelihood because of the central theorem. So in this sense, power spectrum and bispectrum is more kind of stable and robust against this noise. But for field level inference, there's some challenge. What is a correct likelihood or whatsoever? So this is summary. Essentially, field level inference is equivalent to the power spectrum plus bispectrum analysis. And in terms of the cosmological parameter constraint, they are kind of similar. And how to treat these non-Gaussian stochasticities, there's some challenge in the field level inference. That's it. Thank you.